Okay, so here we are. We had example 410 for my class 16 at the University of Hartford in Thermodynamics. So let's read it. Steam at 1.4 megapascals, 300 degrees Celsius, is flowing in a supply line with three different insulated things, right? So these little vessels that are going on here. This guy, this guy, this guy, and this guy. And I'm going to go to the laser pointer. And the valves on the empty systems, right? So these are all empty, are opened. They fill up to the supply pressure. So this we're calling what's inside this pipe the supply pressure, and then the valves are closed. So this is the transient thing that's taking place. These were empty. This is completely empty. This one, the piston's all the way up, and this one, the piston's all the way up, and it's got some kind of force coming in there. We neglect kinetic energy and potential energies, and we want to determine the final temperature for all three cases. And remember, these are all insulated, so I guess that's what the little fuzzy little gray thing around that is supposed to be. And here's some more description. Rigid tank and device A is somehow magically mass is 0 inside, and the volume is constant. That's not true for this one because the volume will increase. It starts out kind of at 0, right? And it's also a spring-loaded thing. So taking a look at this, you can see that the pressure, and they're saying because of the spring, the pressure is going to be a linear pressure, a linear spring, right? So it's going to operate like some constant times the volume. And they're even telling you what that constant is going to be. This A is the piston area right there, if you were wondering. And let's see, and the pressure is equal to 0 in the beginning. There's no place for there to be a pressure, and the mass is equal to 0 in the beginning. And then lastly, they have a thing here where we have a force that's being pushed onto there, and I believe that force is in such a way that the it will float will equal the line. Okay, so I guess these pressures are the pressure in the line is always going to be the same right here. So this thing is going to come down and then it's going to hit this stop, and that we know what that volume is going to be. All right, so we want to try to, with these parameters, 1.4 megapascals, 300 degrees Celsius, we want to try to figure out what these temperatures are. It's not as tough as it might appear in this first crazy thing. None of these problems are as difficult as they sound in their statement. You got to kind of like first take it on faith that you can solve the thing, and then just start plugging and working through until you navigate to a place where you can kind of go, oh yeah, okay, I see what happened there. So we're basically just looking for find, as I wrote on my thing, find T2. Right, so if we're going to take a little trip to table B 0.1.3 because this is superheated right here. And we go at that pressure 1 of 1400 megapascals and T1 of 300 degrees Celsius. We're going to find, I guess I decided to write them all down. I don't know if I need all of them, but I got all of them, right? So all the things that we've been doing so far. We haven't done entropy so far, so we don't need that. But we got internal energy, enthalpy, so 3040.35. We're for sure probably going to need that one. We're for sure probably. Is that a thing? And then I also put this down because there might be something where we need the mass and we know and we might know the volume. So let's go ahead and get that down. All right. So the main idea that's going on here at one level, let's say where they wrote down the equation that they said was E2 minus E1. So that's the energy inside the control volume. It's going to be the Q going across the control volume. And notice this is not a dot, it's not lowercase. So this is just a chunk of energy, right? And they wrote a control volume, so I'll write control volume, but it's kind of understood. All right, so this is stuff that's passing across the control volume. And then they have the summation of MI, HI, and they said that the potential energy. So I'm going to leave this off, and I leave this off a lot, unless there's some real reason to write this whole thing out. I wouldn't bother writing it out. It's only when you know something about the velocity, or that's like one of your objectives is to have that velocity. And if you know something about the potential energy, by all means use it. But we often are neglecting those. We'll pick up on some of those things in fluid mechanics, so they don't just go away forever. Some things we know about this situation here. First off, it's insulated, right? So this is what that means, right? So there might be some heat exchange going on, but it's all internal to this thing. Nothing crossing the control volume. There's no work crossing the control volume. Ooh, I don't know if I want to do that. That might not be fair to say for all three instances. It's really only true in the first one. All right, so I don't want to just ram through. All right. But we also know that for this one, M1 is equal to 0. M1 here is equal to 0. M1 to so M1 is equal to 0. That's a good thing. What else do we have right here? And okay, I guess I'll just go device 1. And I might use more paper because it's going to be tough to cram everything in. So device A. In this case, we already said that that's true right here. And then we're going to say that the work was equal to 0. Okay. And so what we're basically going to say, okay, and then over here, we could say that the energy that we're using, right, the energy is going to be mass times U right there. It's going to be equal to, I guess maybe I should write as big U. Big U, which is going to be mass times little u. And so for this one right here, there's no mass inside here. Since there's no mass inside here for one, E1 is, since M1 is equal to 0, E1 is equal to 0, which means little u1 is equal to 0, so we're fine right up there. So basically with this whole equation right in here, and we said there's no mass exiting. So ME is equal to 0, right, as well. And I think that's the case for every one of these things across here. So what we're left with in this device is MU, M2, U2 is going to be equal to, and then you go MI, MI, HI, right? So the enthalpy entering. So therefore, what we will find here, let's see if I can say this correctly right in here, that you could say, and then you know that M2 is equal to MI. So these are going to cancel out. So U2 is going to equal to H entering. This is the entering, the I. Incoming, maybe. I don't know what the I is for. And in, maybe that's in right here. So what our goal is to find the temperature. Well, we know this enthalpy right here. That's the enthalpy coming in. So this is going to be the enthalpy afterwards. So what we could do is just look it up. So let's go and I guess I can open up my book. Sure, I own a book. I can own it. It's not a great copy. It's a pretty decent book. Okay, so we don't know if it's superheated or not, but let's go ahead and just take a guess that it's superheated and look that thing up and try to find. Okay, so and we're gonna assume, well, it's gonna come to that pressure, right? They open the thing up, they let it fill up, and then they close it, so it's gonna come to that pressure. But we don't know what's going with that temperature, right? We let it come to the pressure, but we didn't let it get to everything to stabilize out. So what we just said is we have reasoned out that the internal energy is going to equal the enthalpy coming in. So at that pressure, and they didn't do us any favors by going that no, I guess they did 1400. So there's 1400 right in there. What you need to do now is find that 3040, which is right over here for that 300 degrees, for 300 degrees, right? But now we've discovered or decided from this transient process that the internal energy is going to equal that. So we're going to come down to there. So it's going to be somewhere in between 400 and 500, right? Because we're looking for 3040 in the internal energy right up in there. So that's like the idea. And so if you interpolate, you'll find that at that point, sorry, so I'm going to write down T2. T2 is going to be equal to 452.1 degrees Celsius, right? So that's kind of an interesting thing. The temperature goes up in this process. We have, remembering what we're doing, we have this line of supply that's magically, no matter, even if when we open a valve, it doesn't change. The supply is just that controlled, that good. It's a large supply, so it'll just fill this tank up. As soon as it gets to 1400 ps, did they say it's supposed to be kilopascals? I don't know what the hell I was writing there. Not 1400 megapascals would be a lot. And it should be, okay, 1.4, yeah, okay. So anyway, that's the first idea. The second idea here, all right, so there's the device A. Device B, we're going to have this spring thing going on there, and they tell us that it's acting linearly, right? So you could even just plot the thing out of a P versus V, and it's going to, I'm starting to think right here. No, it's going to go upwards, right? So the P versus V, because it's going to start at 0. Let's yeah, I guess, yeah, they decided to start, I don't know. You're going to go like this right here, right there, right? So we're going to get a triangle this time, not a trapezoid, I guess. I don't know if we're starting in a vacuum in space, but I suppose that's what we're trying to say. No, we don't care about apparently the force underneath there. So the work that we're going to get right there is going to be integral P dV, and so we're going to equal really 1/2 P times V, the volume of the thing. So I guess magically there is no pressure in there. All right, so coming back up into here and looking across right there, we still have the same conditions where we have no E1 because there's no there's no M1 in there, so it's just right here. So we're going to write out, I'm going to rewrite the things that do apply here. So we're going to have MU is going to be, so this is MU, I'm sorry, I'm trying to write down the numbers. I didn't have them written down. The book let me down. So I think it's M2U2. It's going to be equal to negative W. That's crossed. This is the work. That's because of the spring. And then it's going to be plus M coming in, right? And times H coming in. And so if we do this, we can also, all right, so what I could have set up here, we could also say that's 1/2 P M specific volume, right? Because you could, we could replace this volume with the M times there. Okay, so I guess I'll write it again. And this MI is equal to M2, just like above, right in there, because it's coming in. So U2 is equal to negative 1/2 P, I'll put the V there, M, and this is 2 plus M2H coming in, right? So all these M's cancel out. And what we're going to find, sorry, I'm looking here. Just one second. Let me pause. Okay, so here's what here's the thing. All right, so it's sort of a trick. What you're going to do is you're going to take U2 is equal to, I'll write it again, negative 1/2 P V2, right? P2 V2, plus HI, right? So what it says is that U2 plus 1/2 P2 V2 is equal to that incoming HI. So we know this value right here. It's this value. But we're going to have to look into the steam tables, right, to be able to find some properties combination. We know P2. We're going to assume that's the 1,400 kilopascals. But we're going to look for, in the steam tables, through trial and error, a combination, a thing that has the properties, when you put these together, that equal this. And you may need to interpolate to do it. So this was kind of a pain in the ass thing to do. I did it. I'm not going to rewrite it, because I just remember what I did. So here's what I did right here, okay? Is I narrowed down what I thought it would be. It's somewhere between 400 and 350. And here's the U and the V at those locations. So I put that U and that V back into this equation up here, U plus 1/2 P times V, and then it ended up equaling this amount. And then I did it again for 350, and it was this amount, and and the value that we want, the 3040, is in between these two, so I could interpolate this with these two values and find what temperature lies in between there. So that was a lot of words, but let's go back and see what we had done. We opened this valve up, and it pushed this pressure started to fill this up and push this down, and we knew its behavior because of the spring, right? And we knew that it was linear, and it was basically going to be a triangle, so it's going to be 1/2 pressure times volume, right? And then going through this with the transient, for this transient process, we isolated down that after canceling everything out, that the U was going to be equal to the original enthalpy minus this. So we could go bring this over to the other side, and now be on the lookout for where some combination of internal energy per mass and specific volume, when you put it together in this way, ended up equaling that initial thing. So it's not a practical problem, but it's a conceptual problem in terms of how to break down and think your way through this, right? So we have another one here. Already nobody's going to be watching this video all the way to this point, but I figured I would try it, try to explain this a puzzle that they've presented to us, where we have this force right here, and that force is loading this cylinder, and it's in such a way that it makes the pressure constant. So it's constant all the way time until it comes down to these stops. And when it comes down to these stops, we're able to, it's full of mass, and we close this valve up. Now we want to see, when does it, at what temperature does it stop? Now this is a really stupid one. I forgot how stupid this was for this device. But anyway, so what we'll see here, when coming back up to our main equation right here. So let's write that down. The limited amount that we need for here, device C. We do have work in this case, right? Because we have force in a distance, and so we go, the work is going to be the integral of P dV, right? And so, but the way that we've worked this thing out, no pun intended, is we're going to have zero volume at the beginning. So it's just going to be P times V2 minus 0, right? Because it's a constant pressure. So right there. So that's going to be the same thing as this, which is the same thing as P V2M. And then so when we come back up to the top here and look at this, and we go, okay, so we're going to have M times U2, I guess M2, U2, it's going to be equal to, and we're going to have, we got no heat coming in, but we do have this right here. So we're going to go minus PV2M. I guess we could put a 2 there if we want to, who cares? And then lastly, we're going to go plus MIHI. All right. Well, the masses cancel out because that MI becomes the M2 because it's entering right here. And what you're left with here, you could rearrange this and go HI is going to be equal to U2 plus PV2. And that ends up being the definition of enthalpy. Right, so this is the enthalpy. This would be U2 plus P times V2 is the definition of H2. So what we find out is H1 equals H2, and therefore the temperature must be equal to 300 degrees Celsius. Did you follow that? Try it again. Here is the equation we're using for a transient process. This is a transient process in which way the force is going to make it so the pressure inside this cylinder is always equal to this. So it's a constant pressure all the way coming down to some volume, and they don't even bother telling you what that volume is. But when working through this equation right here, we already said E was going to be 0 because there's nothing inside the cylinder, so it can't be. No heat transfer is insulated. There could be some work. There could be mass coming in and the enthalpy of it coming in, but there's no mass exiting. So all we're left with is E2. Oh, cross that out. E2 work and mass times this. And we said that the E2 is going to be internal energy in this context. All right, so we've written out this for the thing, canceled out the masses, and move this minus over to the other side. And we find that the enthalpy, the internal energy at the end plus the pressure times the specific volume at the end, those we know that's the thing, that's the definition of H right there. So that's going to be H2. So H2 equals H1, and because of that, our conclusion is the temperature must be equal to what the temperature of the supply. Wow, what a lot of words. Hopefully this goes better in class. I don't even know if I want to do this example. This example is not in the 8th edition. It is in the 10th edition. So I was thinking about maybe just not doing it. I recorded a video, so I think I can skip it. It's not really a practical problem. It is a conceptual, so sort of like brain games. But I don't know. Are you better off for having seen it? Maybe.